The world's oceans are a vast and mysterious expanse, and beneath their surface lurks an invisible armada. Right now, at this very moment, an unknown number of submarines, stealthy, silent, and armed with the most advanced weaponry ever devised, are gliding through the depths. From nuclear-powered ballistic missile-armed submarines capable of wiping entire cities off the map, to attack submarines stalking their targets from the darkness of the ocean floor, ready to cripple their enemy's surface operations. These vessels operate in a realm beyond civilian sight and often beyond accountability. Just last year, a Russian Kilo-class submarine was detected inside the Philippines' exclusive economic zone and had to be escorted out by the Philippines Navy. Every major naval power maintains a fleet of these submarines, and every major naval power has invested billions of dollars into detecting and destroying these dangerous machines. This technological battle is coming to a fore in the seas surrounding Taiwan, where China is currently building what is being dubbed the Second Great Wall of China, the Great Underwater Wall of China. This wall isn't designed to stop the advance of Mongol hordes, but designed to detect and locate even the stealthiest of submarines. One of the many new technologies being deployed around the world to even the battlefield against these powerful submarines. Since 2016, China has been operating 2 underwater sensors, one located in the deepest point on Earth, Challenger Deep, and another off the coast of Yap, Micronesia, both within earshot of America's farthest flung military outpost in the Pacific Ocean, Guam, and directly on the path through one of the primary entry points into the South China Sea. These sensors have been tracking US naval movements for nearly a decade, and that program is being expanded to cover the entire maritime border of China, to ensure submarines cannot enter Chinese territory without being detected, something that could cripple an amphibious invasion of Taiwan before it even started. This Great Wall of acoustic sensors are currently being installed at an estimated cost of $300 million, and China has not been shy about sharing their new capability, with videos of the installation process and scaled models of the system being shown off on national Chinese news. Each of these devices that we saw fiber optic cables being attached to by an ROV is a sonar array. These are active devices that send pulses of sound and wait for a return signal, with 3 of them being attached to a primary gateway, allowing them to precisely triangulate the position of anything within range. The system also incorporates hydrophones, passive detection that simply listens for intruders. While nations around the world have spent billions developing ultra-quiet submarine technologies, this system prevents an enemy from being able to locate the sensors through those sonar pings, which are audible to their target. Each cluster of acoustic sensors are estimated to have around a 160-kilometer range, and China is expanding that system to cover every entry path into the South China Sea. The system is powered through cables linked to onshore facilities, delivering 10 kilovolts of high-power direct current, while each of the sensors are connected by optical fibers, allowing data to be quickly shared and analyzed. Incredibly, there also appears to be a charging dock incorporated for an underwater drone, which may be for system maintenance, but could easily be used to power autonomous drones designed to attack submarines. One of the many areas of technological development under focus by naval powers around the world, but more on that later. This is a massive undertaking. This scale model depicts the system as it was installed and tested off the southern coast of Hainan, which is also one of China's primary submarine pens and a vital part of their force projection into the South China Sea. Detecting a submarine is simply the first part of countering them, and there are many more ways of unmasking these machines as they lurk below the surface. Sound isn't the only way. This is the Lockheed P-3 Orion, one of the primary tools in the United States submarine hunting arsenal, and one of the few planes in the United States military that has been in service for over 50 years. It can carry a huge range of anti-submarine weapons like the Mark 50 torpedo. It was specifically designed to attack deep-diving submarines, and its primary design feature to allow it to complete this task is its propulsion system. We need a high energy density power source to achieve the speeds and range needed for a weapon like this. But there's one major problem for a device designed to dive to the extreme depths that submarines dwell in. The pressure outside the torpedo continually rises, and eventually that pressure is going to be higher than the exhaust pressure of the engine. This can be solved by actively pumping the exhaust out, but there is a more elegant solution: storing the exhaust products on board. For most combustion engines, this is a recipe for disaster, but with the right reactants, it can work. This torpedo is powered by a lithium fuel and a sulfur hexafluoride oxidizer, a highly unusual fuel oxidizer combination, but they have one critical property. The volume of the products of combustion is smaller than the volume of the reactants, allowing them to be stored on board without any pressure buildup. The reaction occurs inside a boiler where the heat generated is used to create steam, which drives the propeller. The steam is then driven to a condenser mounted on the outside surface of the torpedo, where it can be cooled by the surrounding water rushing by, and then returned to the boiler as liquid water. This system also means the torpedo does not have an exhaust wake, making it harder to detect. However, the P-3 is rarely used in an offensive manner. Its primary role is in reconnaissance, and one of its most distinguishable features is this huge pole sticking out of its rear stabilizer. This is a magnetic anomaly detector. It searches for the tiniest disturbances in the Earth's magnetic field. The hull of a typical submarine is made out of ferrous materials that become magnetized by the Earth's magnetic field. This induced magnetic field then disrupts the relatively constant distribution of the naturally occurring magnetic field. There are a couple of methods to measure magnetic field anomalies like this. We have quantified the strange induced magnetic fields of Europa using a fairly simple magnetometer. It consists of a base coil wrapped around a metallic ring core. On one half of the ring, the wire coils clockwise, and on the other half it is wrapped counterclockwise. Another measuring coil is placed on top of this ring to measure the magnetic field running through the core. Without an external magnetic field, the magnetic field generated by these opposing coils would cancel each other out. But when placed inside a magnetic field, the core has a slight bias in the external field's direction. This can be sensed in the outer windings and measured as an electric current, allowing us to detect magnetic fields with precision, but not enough precision to detect a submarine. For that, we need a device with an incredibly high sampling rate and sensitivities as low as 0.001 nanotesla, 50 million times weaker than the Earth's magnetic field of 50 microtesla. To measure this, we take advantage of light and its interaction with helium atoms. Helium atoms interact with infrared light at a precise wavelength of 1085 nanometers. When a helium cell is placed between a laser of that wavelength and a photodiode, the atoms absorb the light and jump to a higher energy level. As they relax, they emit light in random directions, reducing the amount that reaches the detector. But this changes when the atoms are exposed to a magnetic field. Their energy levels split into three, with the energy gap between them depending on the strength of the magnetic field. This is known as the Zeeman effect. Now, when the laser shines on the helium, atoms can still be excited, but as they relax, they may fall into any of the three levels. The key is that 1085 nanometer laser can only excite atoms from the middle level. Eventually, the laser depletes that level, leaving fewer atoms available to absorb the light. As a result, the helium cell becomes transparent, a condition called the optically pumped state. To measure the magnetic field, we add a radio frequency pulse tuned to the energy gap between the levels. This pulse repopulates the middle level, letting atoms absorb the laser light again. This results in a dip in the detected light, but only when the pulse's frequency matches the energy gap. At the average magnetic field strength of the Earth of 50,000 nanoteslas, the corresponding frequency is 1.4 MHz. At 50,100 nanoteslas, it's slightly higher at 1.43 MHz. By constantly sweeping the range of frequencies and observing when light intensity drops, we can precisely determine the magnetic field strength perpendicular to the helium laser axis. With three detectors aligned along the X, Y, and Z axis, we can map the magnetic field in 3 dimensions. However, even with this technology, it's not easy detecting a magnetic field anomaly this small. The ASQ81 magnetometer is typically housed in a boom or tail stinger extending from an aircraft to minimize interference from the aircraft's own magnetic field. Chances increase drastically the closer the detector is to the object causing the anomaly, so deeper diving submarines are much harder to detect. Because of this, the P-3 is most effective at low altitudes, forcing it to fly at 500 feet or lower, while it follows a systematic grid search pattern. This is a useful tool that appears in every large Navy arsenal, but for every military technology that develops, a counter is also developed. Not all metals are ferromagnetic. Titanium is diamagnetic, meaning it has an extremely weak effect on magnetic fields, so building a submarine out of it is extremely appealing. There's only one problem. Submarines are gigantic, and we can't easily weld titanium because it oxidizes extremely quickly when exposed to heat. This was a problem that Grumman faced while manufacturing the F-14's titanium wing box. Grumman had to custom build an electron beam welding device that removed oxygen from the build area and provided the heat necessary for welding with a concentrated beam of electrons. Now imagine how confused the United States was when reports began to emerge of Russian submarines with hulls made entirely out of titanium. In 1969, sightings began to emerge in the Never River of new ultra-small nuclear-powered submarines. At just 79 meters long, it was the world's smallest nuclear submarine at that time. But that wasn't the most unusual thing about it. Its reserve buoyancy was about 3 times higher than that of American equivalent submarines, meaning about 30% of its volume lay above the water's surface when its ballast tanks were emptied. And its surface was much more reflective than a typical steel hull. Both of these facts pointed towards the Soviets using a new material, titanium. If this was true, it was a major technological development. Titanium's strength-to-weight ratio would allow the submarine to be lighter, smaller, stronger, faster, and capable of diving even deeper than its steel counterparts, while being extremely difficult to detect with magnetic anomaly detectors. This news shook CIA analysts. A submarine that could dive deeper and avoid being detected was a major advantage. How were the Russians building something this big out of titanium? Many didn't believe it was possible, and the original theorist, Herb Lord, spent the final decade of his life trying and failing to prove it. Analysts believed it was possible for the Soviets to weld smaller titanium parts in hermetically sealed chambers, in a similar way to the F-14's wing box, which also began production in 1969. We are now sure that they did indeed manage to build titanium submarines, something other nations have not managed to duplicate, which is likely why there is essentially no public information available on how they did it. Some websites claim that the Soviets hermetically sealed the entire indoor shipyard and had workers enter through airlocks with what were essentially spacesuits, with their welding equipment in hand. But a search of CIA documents do not support that claim. I would personally assume they created some sort of localized method of sealing off atmospheric air from the weld zone, with some sort of airtight attachment or smaller chambers like the one Grumman created. Creating airtight seals in a small space is hard enough. Doing it at shipyard scale, with all of the contamination that comes with an industrial setting, just does not seem plausible to me. This is a truly remarkable achievement, something the US deemed too difficult and high cost to even attempt. But with any new novel threat like this comes a counter. This submarine could travel at 40 knots while submerged, faster than any NATO submarine, and somehow faster than any torpedo too. The Mark 48 torpedo was developed as a result, capable of traveling at 55 knots. It uses a fuel specifically formulated for torpedoes called autofuel. It's a pretty amazing red monopropellant, meaning the fuel and oxidizer are combined into a single mixture. It was specifically formulated to be stored inside torpedoes for years without any issue, and surprisingly, it's pretty hard to ignite, considered non-flammable and non-explosive under most circumstances, which is unique for a monopropellant and important for a device designed to operate deep under the sea. The torpedo also has a unique propulsion system. It uses something called an axial flow liquid propellant swashplate pump jet engine. That's a lot of words that you probably understand individually, but when combined it becomes a bit of an engineering riddle. Axial simply means the pistons are parallel to the driveshaft, helping reduce the cross-sectional area of the torpedo without sacrificing piston head volume. But this means we need to replace the camshaft that converts the reciprocating motion of the pistons into rotational motion in the driveshaft. For this, we need a swash plate. These 6 pistons then drive the 2 contra-rotating propellers that are shrouded by this ducting and nozzle. This is a pump jet, making this torpedo a scary adversary for any submarine. But first, it needs to find its enemy. It has active and passive homing sonar for this purpose, and when it's first fired, a wire follows it out from the torpedo tube that connects it to the submarine's superior sonar. Its target is to strike near the midriff of the ship. This is a big torpedo with a massive warhead. When it explodes, it's capable of breaking the back of even the strongest titanium submarine. This is what it looks like when it finds its target. Here it is striking the Australian destroyer HMAS Torrens in 1999, and here it is striking the American USS Fletcher during a 2008 RIMPAC exercise. Once a submarine is found, it's not a safe place to be. This is why so much of the battle against submarines revolves around detection and tracking. Much of the major advancements in submarines have revolved around reducing their audio and magnetic signatures, but a new technology has joined the race that needs neither. Space-based synthetic aperture radar, or SAR, and in 2023, China launched 4 satellites that utilized this technology over the Western Pacific to monitor sea traffic. This technology is honestly pretty insane, because they aren't just detecting surface movement. They can detect submarines under the surface by looking for their distinctive wakes that travel to the surface. To do that, the radar has to have excellent resolution to picture fine details, which can be difficult for typical radar as resolution is directly related to the length of the radar's antenna. The equation to calculate the length of antenna needed for a particular spatial resolution is pretty simple. This is the radar wavelength, a lower wavelength results in a shorter antenna. This is the altitude, a higher altitude results in a longer antenna. And this is the spatial resolution needed. Let's say we want a 1 meter resolution with X-band radar. That would need an antenna 25.5 kilometers long. Oh shit. This length is called the aperture, and that's the first clue to how synthetic aperture radars work. They take advantage of the satellite's altitude to create a virtual aperture, basically like a long exposure on a regular camera. As the satellite moves forward, it continuously sends radar pulses and records the echoes. Each pulse overlaps, and the radar will record the same object multiple times from slightly different angles. These pulse returns are then processed and combined, giving us incredible high-detail 3D maps of the world and the ability to detect submarines by the waves they make from space. Technology is catching up with traditional submarines in other ways too. Remember that drone being charged underwater in China's model of the Great Acoustic Wall? That may well be the way of the future. Take Northrop Grumman's Manta Ray drone, which you can see docked on Google Maps right now. It's the true future of underwater warfare. Drones are all the rage right now, but their effects are going to be most pronounced under the sea. Removing people from the equation changes everything. Drones never need to surface. With those underwater power cables, we can recharge them at a hub and have the drones continuously patrol their area. With no need for crushable air inside the hull, we can get more creative with our design choices. First, we can switch from metal to reinforced plastics and lower our magnetic signature. We can use batteries with near-silent electric motors to massively reduce our audio signature. And when needed, they can anchor themselves to the seafloor, turn off all of their major functions, and just enter listening mode. No need for a great wall when you could have a great swarm. These autonomous electric submarines are likely going to make crewed submarines a thing of the past in the not-too-distant future. Keeping on top of changing technology is important for any industry, and today's sponsor, Onshape, fixes a lot of the problems I faced when I was working as a design engineer. Onshape is a fully cloud-based CAD platform, meaning there's no software to install and no outdated files floating around. Everyone on your team can access the latest version of a design anytime, anywhere, on any device. That would have saved me a ton of headaches when I was sending CAD files back and forth with sales teams and suppliers. Onshape also handles compute-heavy tasks like finite element analysis and rendering entirely in the cloud, so you don't need a high-spec workstation to get serious work done. And now, Onshape has launched Onshape Government, a version of their platform that is ITAR and EAR compliant, making it a viable option for defense contractors and any teams working on regulated or export-controlled projects, like a highly secretive drone submarine, for example. Whether you're designing complex systems at work or building parts for a hobby project at home, you can try Onshape for free at onshape.pro/real engineering or click the link in the description.